true projects. In this video, we are going to explain about the project entitled as Osteoarthritis classification using hybrid quantum convolutional neural network. So before getting into the video, let me give you the brief description about the project. This approach combines classical convolutional neural networks with a quantum computing techniques to improve the classification of orthotritis from medical images such as X-rays. The classical CNN extracts high-level spacious features while the quantum neural network process these features using quantum circuits for enhanced pattern recognition. The hybrid model aims to achieve higher accuracy and computational efficiency compared to purely classical deep learning methods. Coming to the abstract, osteoarthritis is a progressive degenerative joint disorder that affects millions of people worldwide, making early and accurate diagnosis essential for effective clinical intervention. The abstract introduced a novel hybrid classification framework that integrates a pre-trained VGG16 deep learning model, a quantum convolutional neural network, and a switch activation function to classify knee orthotitis as normal and affected categories. Unlike convolutional deep learning techniques that rely on classical computational and ReLU activation. The proposed approach incorporates quantum computing principles such as superposition and entanglement to enhance feature learning. Experimental evaluation on knee orthotitis dataset shows that the hybrid model achieves accurate greater than 97%, demonstrating superior performance compared to traditional deep learning methods. Coming to the existing system, the existing system classifications are primarily based on classical deep learning architectures such as VGG16, ResNet, Exception, and other convolutional neural networks. These models depend heavily on ReLU activation function and traditional feature extraction methods, which limits their ability to model complex non-linearity relationship present in medical images. While these approaches achieve acceptable accuracy, they suffer from challenges such as vanishing gradients, limited expressive power, and reduces performance when handling imbalanced data set. Furthermore, classical models are incapable of exploiting quantum characteristics like superposition and entanglement, which could otherwise help capture deeper correlations within high dimensional image data, thereby restricting overall classification accuracy. Coming to the proposed system or base paper work, the proposed system addresses the limitations of existing approaches by introducing a hybrid classical quantum deep learning architecture. In this framework, a pre-trained VGG16 model is utilized as a robust feature extractor capable of capturing rich spatial and texture-based information from knee X-ray images while reducing overfitting. These extracted features are then passed to a quantum convolutional neural network, which processes the data using quantum circuits that exploit superposition and entanglement, enabling analysis in higher dimensional, high birth spaces and improving pattern recognition. Additionally, the Swiss activation function is employed to enhance learning efficiency by providing smoother gradients and better information flow compared to ReLU. As a result, the proposed hybrid model significantly outperformed traditional VGG16 based systems, achieving over 97% accuracy and superior performance in terms of precision, recall, and F score, making it highly effective for knee orthotitis classification. Coming to the dataset, the knee orthotitis dataset is available on Kaggle containing knee X-ray images that are used to identify and classify the severity of orthotitis through automated analysis. Each image is automated using the Kerling-Lawrence gradient system, a clinically accepted standard that categorized orthotitis into five security levels. Grade 0, no sign of orthotitis. Grade 1, doubtful. Grade 2, mild. Grade 3, moderate. And grade 4, severe. These grades are determined based on visual radiographic characteristics such as joint space narrowing, bone surps, and structural changes in the knee joint. The dataset originates from the Orthotitis Initiative, a large scale publicly funded research project focused on understanding the progression of knee orthotitis. Due to its structured labeling and medical relevance, the dataset is widely used in machine learning and deep learning research for both binary classification and multi class classification, making it highly suitable for developing computer aided diagnostic system in medical imaging. Coming to the novelty or extinction or enhancement or improvement. As an extension of the proposed hybrid model, advanced deep learning architectures such as DenseNet 121, AlexNet, and VGG19 were evaluated to further improve knee orthotitis classification accuracy. These models were tested to analyze their ability to extract richer and more discriminative features for knee X ray images. Among all the architectures, VGG19 achieved the best performance with an accuracy ranging from 98% to 99%. This improvement is mainly due to VGG19's greater network depth, which allows it to learn more complex and detailed feature representations than VGG16. The deeper architecture enhances the model's capability to capture subtle pathological changes in knee joints. When combined with quantum enhanced learning concept, the extended model demonstrates superior diagnostic accuracy. The enhanced confirmation the effectiveness of deeper CNNs in hybrid quantum classical orthotitis classification system. Next, as an extension, the Flask framework is used to develop a user friendly interface that allows users to provide input data for prediction. The inputs are pre processed and passed into the trained model based on the dataset. The prediction results are then displayed through a web interface, making the system easy to access and use. Coming to the workflow, first we have dataset loading. This module loads the knee orthotitis dataset from a local directory. Images are organized based on severity grades, where grade 0 is considered normal and grade 3 and 4 are considered affected. The dataset is filtered to perform binary classification and split into training and testing sets. Next, data pre processing. In this module, input images are resized to match the VGG16 input dimensions. Image normalization and augmentation techniques such as rescaling, rotation, and flipping are applied to improve generalization and handle dataset imbalance. The labels are encoded into binary form. Next, feature extraction using pre-trained VGG16. The pre-trained VGG16 model is loaded without its fully connected layers. It acts as a powerful feature extractor, capturing spatial and texture based features from knee X ray images. Freezing initial layers helps reduce overfitting and training time. Next, feature flattering and reshaping. The extracted deep features from VGG16 are flattened and reshaped to make them compatible for quantum processing. This step bridges classical deep learning outputs with quantum neural network inputs. Next, quantum convolutional neural network layers. This module implements the QCNN where classical features are encoded into quantum states. Quantum circuits apply convolutional and pooling operations using superposition and entanglement, allowing high dimensional feature interactions. This enhances pattern recognition beyond classical CNN capabilities. Next, swish activation function. The switch activation function is applied to introduce smooth nonlinearity compared to ReLU. Switch improves gradient flow and learning stability, especially beneficial in hybrid classical quantum architectures. Next, classification layers. A fully connected dense layer with a sigmod activation function performs binary classification, predicting whether the knee image is normal or affected. Next, model compilation. A hybrid model is compiled using optimizer, loss function, and evaluation metrics like accuracy, precision, recall, and F score. This step ensures efficient learning and robust evaluation. Next, model training. This model is trained on the pre-processed training dataset for a defined number of epochs. Batch-wise training is used to optimize memory usage and convergence speed. Next, model evaluation. After training, the model is evaluated on the test dataset, performing metrics such as accuracy, precision, recall, and F score are computed and compared with traditional VGG16 press ReLU models. Next, performance comparison and analysis. This module compares the proposed VGG16 plus QCNN plus Swiss hybrid model with existing deep learning models. Results demonstrate improved accuracy and better generalization capability. Next, result visualization. Training and validation accuracy or loss graphs are plotted to analyze conversion behavior and model stability. Coming to the front end, a front end of the system is developed using the Flask web framework, providing a simpler and interactive user interface for knee orthotitis prediction. It includes user registration and login functionalities with credential security managed using a SQLite database. Users can upload knee X-ray images through the interface, which are then pre-processed before being passed to the trained models. The prediction generated by the trained hybrid model is finally displayed on the front end, allowing users to easily view and classify the results in a user-friendly manner. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework is Python 3.7.2, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project. Firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then open command prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the command prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. This is the home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button and Get Started button. Firstly, click on Get Started button so that Create an account will be opened, where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a password. Then click on Sign Up so that all the given details are stored in signup.db and login.html will be opened, where you need to access the application by entering username and password. Then click on Sign In. The prediction page has been displayed. In this page, we have orthotitis classification using test image button, graphs button, notebook button, and logout button. Firstly, click on classification button so that the form will be opened where you need to upload the X-ray image to analyze and classify orthotitis using advanced quantum computing techniques. Here we need to upload the image. The image has been uploaded, then click on classify so that the input image is pre-processed and the output is displayed as normal, which means the given input image is normal, indicating healthy. We also have the recommendations like maintain health weight, regular exercise, balanced nutrition, and regular checkup. We have it is normal knee joint detected and quick tips are given. Here we have upload another image button and view analytics button. Click on upload another image button so that the form will be opened again. We can upload another image. The image has been uploaded. Click on classify so that input is pre-processed and the output is displayed as affected, which means it requires attention. Orthotitis changes has been detected. We have the recommendations like consult a specialist, medication management, physical therapy, weight management, and pain management. We also have some quick tips and safety disclaimer. Now click on graphs so that the graphical representations of the project will be opened. And let us check one by one. First, we have the class label graph. The graph illustrates the distribution of samples between the normal and affected knee orthotitis classes. It shows that the normal class contains more images than the affected class, indicating a class balance in the dataset. This imbalance can influence model performance and highlights the need for effective feature extraction and learning techniques. Next, we have confusion matrix graph. The confusion matrix shows that the model correctly classifies 108 normal and 91 affected cases, indicating high prediction accuracy. Only one affected case was misclassified as normal, and no normal classes were wrongly predicted as affected. This demonstrates the model's strong classification performance and reliability. Next, we have accuracy graph. The graph compares the classification accuracy of three different models using for knee orthotitis detection. The proposed VGG16 QCNN plus switch model outperforms the traditional VGG16 plus ReLU, while the extended VGG19 plus QCNN plus Swiss achieves the highest accuracy of 99.5%. This demonstrates the effectiveness of quantum enhanced learning and deeper architectures in improving model performance. Next, we have precision graph. The graph illustrates the precision performance of different knee orthotitis classification models. The proposed VGG16 plus QCNN plus Swiss model shows improved precision compared to VGG16 plus ReLU, while the extended VGG19 plus QCNN plus Swiss achieves the highest precision of 99.54%. This indicates a significant reduction in false positive predictions with the hybrid quantum enhanced approach. Next, we have recall graph. The bar graph compares the recall rates of three models: VGG16 plus ReLU, proposed VGG16 plus QCNN plus Swiss, and extinction VGG19 plus QCNN plus Swiss. The extension VGG19 plus QCNN plus Swiss achieves the highest recall, indicating superior ability to correctly identify positive cases. Both proposed models outperform the baselines VGG16 plus ReLU, showing that adding QCNN and Swiss activation improves recall performance. Next, we have F-score graph. The bar chart compares the F-score of three models VGG16 plus ReLU, proposed VGG16 plus QCNN plus Swiss, and extension VGG19 plus QCNN plus Swiss. The extension VGG19 plus QCNN plus Swiss achieves the highest F score of 99.4964%, showing a clear improvement over the other two models. Overall, adding QCNN and Swiss along with this using VGG19 enhances performance significantly. And then click on Logout. So finally, the proposed hybrid quantum convolutional neural network effectively classifies orthotitis with highest accuracy, leveraging both classical and quantum features for enhanced performance. The model demonstrates robust capability in detecting disease severity from medical imaging, outperforming traditional approaches. This approach highlights the potential of integrating quantum computing into medical diagnostic for more precise and effective analysis. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.